is Saeed Danesh. I'm a technical project specialist with REHAU, and I work out of our sales office in Vancouver. So to any of my fellow Canadian friends, hi. It was a long trip, I know, but it's always good to be here. So at REHAU, we manufacture the high-end quality of XA pipe, which is used in different applications like radiant heating, cooling, plumbing, geothermal, and also the district heating energy, as well as the snow melting and projects like that. And besides that, we offer high-end and top-notch engineering services. And we are very involved with organizations like ASHRAE and CBE, because we totally believe that the innovation and the progress happens through these collaborations. We're hoping by these collaborations to boost the research and development on topics like radiant heating and cooling, kind of to push the boundaries on, let's say, high performance building by getting the more energy efficient buildings and also the highest level of the occupant comfort. And about CBE, I'm gonna pass you to Carlos, my friend.
Thank you, Saeed. So I'm Carlos Duarte. I'm an assistant professional researcher at the Center for the Built Environment at UC Berkeley. And the Center for the Built Environment, or CBE for short, is an industry and university collaboration research center established in 1997 with some support from the National Science Foundation. And our mission is to improve the environmental quality and energy efficiency in buildings. And we accomplish this by not only studying promising innovations, technologies, design strategies, but also how people use and interact with buildings with these various innovations in place. And because at the end of the day, many of the buildings that are there is to provide shelter and a healthy and a productive environment for people. And to stay true to our mission, like Saeed said, we have a wide range of industry advisory board members who sponsor and direct our research. And if you are interested in becoming a member or want to just learn more about it, come talk to me afterwards. You can also talk to Saeed to learn about their experience as a member. And I noticed that we also have a few members around in the crowd too, so you can find them out and talk to them.
Thank you, Carlos. Thank you. So today we're going to talk about principles of radiant cooling systems, and also kind of highlight the top, let's say, thermal comfort and efficiency as like the highlighted, let's say, advantages of these systems. And then we're going to go through some of the researches that CBE did, especially the solar gain impact and the impact of ceiling fans on the total system performance. And we're going to wrap it up with some of the design tools that, again, CBE developed by some of the project references that some of them we work together, some of them it's been finished for a few years, but those are like some good project reference of REHAU on radiant heating and cooling. And then we're going to open up for any potential questions. Please feel free to ask after that. About radiant cooling systems, technically any system that provides the heat transfer, more than 50% of the heat transfer to the occupant through short wave radiation, we can define it as radiant systems. And normally this is achieved through a network of the pipe. It's either embedded in the surfaces like floor, wall, or ceiling. But if I want to go through the category, these are the three main categories that we divide the systems. First would be ESS, or I call it a unidirectional heat transfer, where one side of your slab or one side of your surface is insulated, and heat transfer happens on one side only to the occupants of the room. Second would be thermally activated building surfaces, or AKA tabs, which is a bidirectional heat transfer. It's on both sides of the slab. And the last is the ceiling panel, which are very popular in Europe. They are gaining momentum in North American market. It's technically a metal plate with the pipes attached on the back. But today we're gonna mainly talk about the two first topics, especially the first one, which is probably more than 97% of the projects that we deal with. So, embedded surface system. How does this system work? In the heating mode, this is what happened. Like three types of heat transfers happen there. We're sending warm water. I emphasize the warm water. We're not talking about hot water. It's the ranges of like 100 to 120 degrees Fahrenheit. So I have a hard time sometimes switching back from imperial to metric. It's gonna be around like 50 degrees maximum Celsius. You send the water through the network of the pipe, some sort of a conduction heat transfer happens there, and then we try to get the temperature of the surface to the level that it starts radiating towards subjects in the room, towards the surfaces in the room, and towards the occupants. That photo actually is a very nice nice one taken by an infrared camera. It's for an operating radiant heating system. The nice thing about this system is if you look at that, for the different areas in the room, the temperature was measured and it was around 69 degrees. So it shows the minimum thermal fluctuation. That's one great advantage of radiant systems because it's targeting the surfaces in the room. How does the radiant cooling system work? It's the opposite way. We are trying to bring the temperature of the surface, especially the floor, down in a way that the other surfaces in the room, other occupants, other objects in the room start to radiate towards that colder surface. So this is a nice photo of ESS system. You see one side is insulated, on the other side the floor is cold enough. I'm going to talk about the temperature ranges and everything, but it's cold enough to absorb the heat from the bodies, from the surrounding area. And this is a photo that shows you that TAB system, which is the thermally activated buildings. This is a very unique type of application. We have a couple of project samples on this. And it's very, very nice because it will act as a radiant floor cooling system on one side, and it will act as like a radiant ceiling system on the other side. So it's working on the both sides. But the reason that we highlighted this section is when it acts as a ceiling system, takes advantage of the natural convection because the air goes and become in contact with the chilled ceiling, and by the definition of let's say getting a little bit colder, it drops down. So that helps with the performance as opposed to the top one. If it's in a radiant heating mode, it helps a lot with the natural convection. So these are the two ways that we do. As I said again, more than 95%, it's like one, let's say, unidirectional heat transfer to the space. The big thing about radiant systems, they are always part of a hybrid system. What do I mean by hybrid system? There is a DOAS system involved. There is a dedicated outdoor air system involved, like a air handling unit. So if one of you guys come after this session and say, okay, you want to use it in my home, I would be, no, please. So you will need a air system. So why you need an air system on this? First of all, radiant cooling system is a limited, let's say, source of cooling. By that I mean it can address, at the good day, whole sensible load or a portion of sensible cooling load, but you need air system to cover the latent cooling load, which is technically the moisture in the air. And also, based on the ASHRAE 62.1, you need some sort of fresh air. Say we have a radiant cooling in this room, we need to provide certain amount of heat, let's say air change per hour to meet that standard of ASHRAE. That's the second reason. And also the changeovers. Let's say in a shoulder season, in an area that you may feel a little bit cold in the morning, but around noontime it gets warmer. Or let's say in this room, all of a sudden I have like 50 folks coming in. Radiant system is a slow response system. So for those times when you have like a quick, let's say, shift in occupancy, you need air system to kind of back up your radiant application. So these are the three main reasons that I say you always see these radiant cooling application in a hybrid mode. So you will need an air system to go with it. If I want to summarize the benefits of radiant cooling, it's very aligned with the LEED or the WELL designation requirements, where superior comfort is our target by improving the indoor air quality, as well as the energy efficiency. We're going to talk about these two as like the highlighted ones, the advantages, and CBE did a great job on these, on the researches and everything. But there is a big chance that we can hook this with a renewable energy source. I know you guys, some of you went to the previous session, which was about geothermal application. So geothermal is a great match for radiant cooling system. Also, it provides a very good freedom and flexibility architectural-wise. So you're getting rid of lots of bulky convectors like big fan coils, and it opens up the the day view or day lighting, which gains a very good let's say score on lead scoring system. And also the maintenance cost. The system is you run tubing in your floor, you pour the concrete. No one sees the system. There is no exposed part of the system that requires any crazy maintenance. The only part of the system you may check every once in a year is like the manifold. You want to make sure no one took a piece and run away. Everything is still there. That's the only maintenance you want to do on this. So when you are working with this, you are lowering your cost of the filters and the fan maintenance and every other moving parts. Also, last but not the least, is you have a very good control and effective control of your ventilation. So I've seen some cases that they have, let's say, air handling units over the top of the building on this, for example, commercial building. So when there is a cooling demand, that kicks in. But how about a fresh ventilation? When you're talking about hybrid system, the good thing about it is you can decouple these two from together. So radiant cooling addresses your cooling demands, but you have constant ventilation going on with your air system. In that case, your occupants, like students in the room, they always feel fresh and they enjoy, that decoupling topic that I was talking.
So we can start talking about comfort and efficiency, and I'll start with thermal comfort. As you may know, thermal comfort is complex, and ASHRAE defines thermal comfort as that condition of mind that expresses satisfaction with the built environment. But negative qualities are often easier to understand and measure than positive qualities of thermal comfort. So as a result, we often have an engineer's view of comfort where we equate the absence of discomfort or a state of neutrality with comfort. In other words, we try to equalize the heat produced and the heat lost by our body with HVAC systems to produce this state of neutrality. So we think at CBE that the next generation of HVAC systems should go beyond neutrality and start thinking about the HVAC system providing thermal pleasure. But the good news is that the human body can transfer heat in various ways, and radiation is the largest portion with about 62%. And in addition, we can control 4 environmental parameters that can influence the heat transfer in our body, and by extension, influence our thermal comfort. And this is a reminder to say that comfort is not just a number on a thermostat. We can also control relative humidity, airspeed, and radiant temperature. So the building industry has mostly focused on controlling the air temperature and humidity for thermal comfort, and as a result, there's a significant opportunity for improvement. At the Center for the Built Environment, we have conducted studies on long-term satisfaction, and the results show that only 11% of the buildings we surveyed provided satisfactory thermal comfort levels of at least 80% in their building occupants. And this is the metric that is defined in ASHRAE's thermal comfort standards. So when we aggregate all the responses from all these buildings that we surveyed, less than 60% of the respondents responded as being satisfied with the temperature in their workplace. Imagine these low customer satisfaction ratings for companies or other industries. It might be difficult to do business when you have a low customer satisfaction rate. So radiant HVAC systems gives building designers the ability to control another parameter for thermal comfort that is important, and that is radiant systems can control the zone's mean radiant temperature. And by having this additional parameter to control, our research suggests that occupants do indeed tend to have higher thermal satisfaction rates when compared to the conventional all-air systems. And these graphs show various analysis of the same occupant survey that I just talked about that shows the increased thermal comfort satisfaction rate when we were using radiant systems. So we can say that in a space with a radiant system, a person has a 60% more chance of having equal or higher thermal satisfaction than a conventional all-air system. And so Saeed, can you tell us how mean radiant temperature and air temperature can be combined to provide thermal comfort and increase increase the efficiency of HVAC systems?
Sure, Carlos. If I go to next one. So this is a nice graph. I want to explain mean radiant temperature. Like imagine this in this lovely weather, you go outside on the sunny side of the building. In that case, your body would be kind of absorber. You feel a little bit, warm. And the same temperature with no wind or nothing, you walk on the shady side of the building. Now your body has become an absorber. It becomes an emitter in this case. So the surrounding area, like the walls or the floor and everything, is colder than your body. So it starts, getting the heat from your body. So in this case, you are the emitter. That's the definition of the mean radiant temperature, and it means average temperature of surrounding. That's all you're trying to do with radiant cooling. You're trying to lower the temperature of the, for example, wall, desk, anything around you, using the short wave radiation. So your body feels more comfortable and in a good way, feels cold. This graph, this was actually published in 1939. That pink area represents where your body functions in a comfortable range. And you can see that blue dot is representing the radiant cooling application versus a forced air, which is represented by a black dot. You can see when we are taking advantages of mean radiant temperature, surrounding temperature, we can let the air temperature inside the room be a little bit higher than normal. I don't know if you guys have fan coils in your bedroom, in your, let's say, dining room. What's the setting that you put it on in a regular summer day? My point is, if you, for example, try normally to be in a comfortable zone around 74, 75, you can leverage it a little bit higher. So you're using the radiation of your body towards surfaces, and let the air inside to be a little bit, more than usual. And that's what we call it the corrected thermal profile. And using that, you can kind of minimize your air system. And by that, it eliminates the drafty feeling. You're not sitting under a big diffuser. You get like a drafty, bad feeling on your skin. And also, you have a great distribution of heat throughout the space. Because again, every single part and piece in the room acts like a absorbent of the temperature of your body. And as Carlos was talking about it, since over 60-70% of your body heat transfer happens through radiation, you will feel super comfortable in these cases. Another thing we can do with using a radiant cooling application is you minimize your filtration and your ductworks. Again, this follows that topic of opening up the space for architects. That's why architects, they love this system normally. And the fact that you're using a smaller air system, it helps with the air velocity noise and everything. And that's again it can provide 1 or 2 points using, on the WELL or the LEED certification, what they define as acoustic comfort. So these whole topics that I mentioned, it's all about, the comfort that is achieved by a hybrid radiant cooling and air system. But about efficiency, I was talking about the corrected thermal profile. That's one important thing, because when you are calculating your cooling load, you're not targeting a very, very chilled indoor air set point. That's why your delta T between inside and outside is not very big. So first of all, you're saving, the first minute you're saving on your cooling load calculation. Second, you are dealing with relatively warmer supply temperature. For a radiant cooling, what we require in most cases is 60 degrees Fahrenheit supply temperature, which is what, around 15 degrees Celsius. Whereas most of the, let's say, other HVAC systems, they may require way lower temperatures. So most of the chillers, they work better when they're dealing with the higher return water temperature. And also, as I said, since we don't need a very low entering water temperature, it's a great match for geothermal resources like the geothermal heat pumps and stuff like that. Last but not least is the, let's say, heating capacity of the water versus the air. So we have a rule of thumb, we say a 3/4 inch water pipe can transfer the same amount of heat energy as a 14 inch by 8 inch duct. And please consider moving water is way more efficient. It's like if you want to compare the same amount of BTU sending by pump versus a blower fan as an example, you will save 75 to 90% on the electrical energy only. And also, Carlos is going to talk about this. You have opportunities for thermal storage, for the load shifting using the high thermal mass as in radiant system application. I know already you guys may think about this, the condensation risk. Okay, first of all, we don't want it to see in residential application. Second, if you are using it in a commercial application, make sure you are going with a tight building envelope, so minimum infiltration. Second, please define a nice control strategy when you are monitoring the dew point. You're looking for the entering water temperature, slab temperature. So every single of these items are considered in your control strategy. And surface temperature, there is a limit by ASHRAE 55. They don't want you to go below 6 degrees Fahrenheit or 19 degrees Celsius in cooling mode. And in most of the climates that I know, 66 degrees Fahrenheit is way above dew point. So you are safe if you follow that direction. Just to give you a hint, on heating mode, ASHRAE 55 also has a cap, which is 84 degrees, which is almost, I think, 29 degrees Celsius. That's the cap on the heating, but they're very sensitive on the cooling side because there could be a risk of condensation. And again, the relative humidity in the room, very, very important. The way that we calculate this is make sure the coldest part of your system, which is the manifold and the entering water temperature, is always at least 3 degrees above dew point. So say you calculated this room in a normal day, around 55 degrees you have the dew point. As long as you're sending the water temperature at minimum 58, you're not going below that, it shows that your coldest part of the system won't sweat. There won't be any condensation. So these are very important topics to consider to avoid any risks on that side. About the energy efficiency study, Carlos talked about this. They've done a great job reviewing some of these projects. They figured out most of the radiant cooling application, especially the hybrid ones, they save around like 32% less energy. But we have a live example for you guys. I don't know if you guys heard of Infosys building. It's a company that they are very great on the data science and everything. Their head office is in India, in Hyderabad. That's their building. It's two identical buildings, each 125,000 square foot. And one side is VAV only, and one side is a hybrid radiant cooling system, which is a TABS system actually, like double directional heat transfer. If you scan that thing, it will take you to the ASHRAE study in 2015. So ASHRAE did a study on this building. You guys can review it if you scan it, but this is the outcome of this study. Almost 22% more satisfied on the hybrid side, and also around 30% less energy consumption on the hybrid side. That's the overall, let's say, conclusion here. You can see on the first year, they saved around 34% on their energy, and then in the second year, by fine-tuning their system, they achieved 40% less energy. And there it is your 20% difference in the thermal comfort of the occupants. So please check out the project and share your thoughts.
So now we're going to talk about how high thermal mass radiant systems offer great design flexibility, especially as we transition to renewable energy sources and efficient HVAC equipment like heat pumps. As we mentioned earlier, high thermal mass radiant systems have the water tubes embedded inside the concrete layers, such as the structural slab, and this has lots of thermal inertia, and as a result, it takes a very long time to cool down the concrete after we start circulating chilled water through it. So on the left-hand side plot, you see that it takes more than 12 hours to cool down surfaces from 77 degrees to 72. And the right-hand plot just shows you a distribution of these response times for various design parameters for these radiant systems. And it shows that embedded surface systems has a medium response time of 6 hours, while the thermally activated building systems has 14 hours. So it's really hard to control them or try to predict a control strategies that will maintain thermally comfortable environment in the indoor space. However, these long response times after a control action present challenges for control, but it also opens up the opportunities for innovative designs and control options. In addition, radiant systems can do high temperature cooling, as Saeed mentioned. So that is using chilled water that is higher than typical. And this is due because these systems have large heat transfer areas, sometimes involving both the ceiling and surface, like it's in the case of TAB systems. And as you can see in this plot, various studies have shown that radiant systems can use chilled water that is more than 45 degrees Fahrenheit, which is the typical temperature for conventional all air systems. However, they're not always designed to do so. The combination of high thermal mass and the large surface areas opens up the possibility to use more energy efficient HVAC equipment, such as these heat pumps. And furthermore, high thermal mass radiant systems allow us to decouple the HVAC operation from the building occupancy hours. And we can start to think about which of the hours in a 24-hour day might be best to operate the systems. So it might be a time when there's lots of solar energy on the grid, so maybe the price is inexpensive, or you start to think about when the grid emissions of the grid is also very low, so you can target those areas of operation. Or we can use like some design, or we can design innovative systems that you can see here on the right-hand side. So where we can use a heat pump to provide the energy source for a DOAS system, and then use that same heat pump to provide the energy source for the radiant systems at other times of the day. So the same heat pump, lower capacity, providing the energy source for the two systems, and they're not operating at the same time. And this kind of system also allows us more possibilities in which we can use water side economizing to provide the cooled water, and thus further increasing the energy performance of this type of system. And this is possible because wet bulb temperatures, which is an important parameter to design water side economizing systems, are a lot cooler during the night. So what you see in this plot is the wet bulb temperatures at the 90th percentile for the cooling season in many US cities. And depending on the climate, we can even do exclusive free cooling, where we just use the cooling tower, the water coming out of it, use the cool water to provide the cooling energy for our radiant systems. And as I alluded in the previous slides, wet bulb temperatures are not just one point. It's a distribution of temperatures that vary throughout the day, and they're usually lower during the nighttime hours. Here in this plot, you can see that we have a higher potential of using just the evaporative cooling, just using evaporative cooling. As we move to the right, the buildings might be less so, and we have to use some more like a refrigerating cooling. But so just by looking at the wet bulb temperature distribution, we can see that some cities might have evaporative cooling. And to figure out if there is, what is the actual potential of using water side economizing in high thermal mass, we developed a simulation study where we estimated the actual supply chilled water temperatures needed for the radiant systems in order to provide a thermally comfortable environment for the space. So we developed a model that represented a commercial office building with various designs and radiant system parameters. So we set the building envelope to the minimum energy code required by the city's code, and then we varied other 24 total parameters that included window to wall ratio, the orientation, zone dimensions, internal heat gains, radiant system parameters like tube spacing depth, the pipe diameter. But when it was all said and done, we created over 360,000 models to simulate in Energy Plus on the city's cooling design day. And Energy Plus is a research-grade tool. It's free and open source that's been thoroughly validated. So we have good confidence there's high fidelity in the results. So, and after each simulation, we extracted the peak operative temperatures. And if the peak operative temperatures were not at 78 degrees Fahrenheit, which is our calculated upper thermal comfort bound, using the CBE comfort tool, which I'm going to talk a little bit in later slides. If it wasn't at this temperature, then we would adjust the supply water temperature and reran the simulation. And after this process was complete, we collected all the final supply water temperatures for each design variant to do further analysis. And so the main results show that waterside economizing is possible in many US cities. So in this plot, you see the proportion of hours that the cooling tower is able to provide the design chilled water temperatures for the design variant that for a typical, or let me repeat that again. So what you see here is a proportion of hours that the cooling tower is able to provide the supply water temperature for the radiant system design that we modeled. And this is divided by the total hours that the radiant system is able to operate on the cooling season. And so, for example, in California climate zone number 3, which is Oakland as a representative city, we saw that there was 50% of the models that can supply the design chilled water temperature 60% of the time with an approach temperature of 11 degrees Fahrenheit. And the approach temperature is just a proxy of how well the cooling tower is performing. Conversely, if we look at the ASHRAE climate zone 3A, which is representative city Atlanta, at least 50% of the models could supply the model's design chilled water only 10% of the time. So there's a big reduction because Atlanta is hot and humid climate, so there's less possibility to do waterside economizing there.
Miami is even worse.
Yeah, so Miami, there's 0%.
Guys from this neighborhood would forget about it.
But this is not to say that radiant systems is not high performing in Miami. There's still opportunity for cooling load savings, but it can't do waterside economizing.
Can't use the cooling tower.
Yeah, exactly. But in summary, 22 climate zones allows 40% or greater waterside economizing operation with a typical 7 degrees operation approach temperature.
I want to jump in here. So this is a REHAU project, Loyola University. It's one of my favorite projects with around 50% of the exterior being glass. And that's why we selected this for Carlos's part, which they studied the solar gain. And it's a radiant cooling both on the ceiling and the floor. And it's using 200 days per year of natural ventilation. Sorry.
Oh, no worries, yeah, good point. So as Saeed was alluding, under standard conditions, the radiant cooling capacity of radiant systems is about 40 to 50 watts per meter square, which is 13 to 16 BTU per hour per square feet. But as soon as we start introducing, as soon as the sun starts hitting these radiant surfaces, the capacity increases by doubling or even tripling in some of the instances. So we observed this phenomenon through simulation and laboratory studies. So you can see the top plot where it's a simulation study. The simulation shows that the results comparing buildings without solar heating the surfaces and with solar heating the surfaces on the other side. So you can see that under extreme conditions, it's almost tripling the cooling capacity there. And we saw similar results in laboratory studies where the red dots are showing the impact of solar radiation as soon as the direct solar is hitting that surfaces. So you see that huge bump as the sun passes through the experimental lab chamber there. So Saeed is going to talk about some applications.
This is a nice project. CBE did a study on this. They measured everything. It's the NIM Regional Transportation Intermodal Centers, aka RTIC. It's the first LEED Platinum transition station in the world. That dome is 120 feet the atrium, and it's like a translucent roof. How do you say it? Yeah, and it's an example of direct sun exposure for the radiant cooling system. And like conventional thinking, they were like, okay, there is sun gain, let's not do radiant cooling, but it was designed to get 9.5 BTUs per square foot, where in a, let's say, direct sun exposure, it got almost 3 times more, 327 BTUs per square foot. And this is you can find more information about this. It's a nice study by CBE.
So air movement is also a significant factor that affects the heat transfer in radiant systems. So normally in radiant systems, as we mentioned earlier, 50% of that heat transfer is at least radiation, and the rest is natural convection. But if we start increasing that air movement into space, then we can increase the heat transfer on the convection side. And to understand the magnitude of this effect, we developed a 2-phase simulation study where we first derive convective heat transfer coefficients for the radiant system using CFD analysis. Then we use these coefficients in Energy Plus to understand the effects of various radiant system design factors. And for these study, we assume steady state conditions for the tabs system where the ceiling and the floor are the cool surfaces, and we also focus just on the convective part of the heat transfer. And this is just to find the heat transfer coefficients using CFD. And the radiant heat transfer for the radiant system under a stays pretty constant for the conditions we tested, so that's why we ignored it in the CFD analysis. So moving on to the main results of the CFD simulations, here's a plot where the x-axis is the temperature difference between the room air and the cooled surfaces, and on the y-axis we have the resulting convective surface coefficient. And so before I start showing the results of the CFD simulations, let me anchor you with the ASHRAE guidelines for natural convection. So in this case, where there's no fan, and it shows that there's an increasing coefficient with increasing temperature difference. So you see that just ramping up as the greater the temperature difference. And recent laboratory studies also show comparable results with the ASHRAE guidelines for the most part. And our natural convection case using CFD also shows that pretty comparable results. And also the 10 air turnovers per hour. So here we're using the term ATH to signify how much airflow the ceiling fan is recirculating in the air. So it's not an air exchange, it's just a recirculation term here, just to be clear. So it's not until 25 ATH case that we start seeing some effects compared to the baseline natural convection case. And we see about a 50% increase in the surface heat transfer coefficient. And then we see almost more than 100% increase in the surface heat transfer coefficients at 50 ATH, and almost 250% increase when we're using 100 ATH. And 100 ATH is at the ceiling fan's maximum speed, and 25 ATH is at the ceiling fan's minimum speed level. So you can see there's a big drastic increase, but this is not necessarily saying that this is how much the heat transfer increases in the zone. So this is just the surface heat transfer coefficients, and that's why we go into the second phase of the study where we input the heat transfer coefficients that we found through CFD and put them into Energy Plus, and to see what is the effect of using ceiling fan for various design parameters. As you can see here, the radiant cooling capacity, the total radiant cooling capacity of the system increases by up to like 30% as we go to the maximum speed setting of the fan. So, Jay, do you want to talk about some of the applications?
Yeah, I just sneaking some of our project samples, between Carlos's presentation. This is one of my favorite projects in Santa Rosa, California, Sonoma Academy. So this project has everything. It's, awarded first place in 2019 educational facility in ASHRAE Golden Gate chapter. It's LEED Platinum, it needs to be above 80, the scoring point of LEED. It is a zero net energy building. It uses natural ventilation, storm and water recycling for the landscape reuse, and it has geo exchange. We did the radiant heating and cooling on this job. And the engineer was interface engineering using the energy unit intensity of 43 kilo BTUs per square foot per year. And in one of the areas, we were studying the impact of the ceiling fan on the radiant cooling performance, which was in a very, let's say, lower mode of fan. It was about like 15 to 20% increase of, let's say, heat transfer.
And so at CBE, like I mentioned earlier, we develop and maintain several design tools to help building designers at the early design stage. And I will talk about 3 of them today that are relevant to the design of radiant systems. So the first one is our CBE thermal comfort tool, and this is the most popular CBE tool, so it gets widespread use for this tool. So with this tool, a building engineer or building designer can experiment with the 6 most influential parameters of thermal comfort that I talked about earlier to create a thermally comfortable space. So in this example, I showed the operating conditions of a radiant cooling system, and as you can see, these conditions comply with ASHRAE's thermal comfort standards. And we can visually see this with the red dot being in the blue thermal comfort zone. And we can also do the same thing with forced stir systems, and as Saeed explained early on in the presentation, we can use various combinations of air and mean radiant temperatures to create a thermally comfortable environment, but that has implications on how we're gonna design our HVAC system to actually achieve this, these operation conditions in the space. And we can also use it for more innovative designs. One of them that we're trying to do more research on is this system the radiant system coupled with ceiling fans. So as Saeed mentioned earlier, we can raise the temperatures in the room because the ceiling fan also produces a cooling effect to people, so we can raise those temperatures, increase our energy efficiency in the space, and still maintain a thermally comfortable environment. The second tool is the CBE fan tool, and this tool allows you to figure out how many ceiling fans you would need in the space and estimate the expected airflow speeds in the space. And it supports various types of fans with a variety of different specifications. And it's useful when you're trying to design a radiant and ceiling fan coupled system, but it's also useful to just use it with a normal conventional all-air system because, like I said earlier, the increased air movement also produces a cooling effect on people. So the third tool is the CBE RAG tool. It's an interactive design tool for the early design of high thermal mass radiant system. And the primary aim of this is to provide an interface for estimating the performance of high thermal mass radiant systems under steady-state conditions for both heating and cooling, and transient conditions or dynamic conditions on the cooling design just for the cooling aspect. So the steady-state conditions are based on the ISO standards, which is standard practice for many building designers, and this tool facilitates those calculations. The tool takes inputs such as radiant system type, supply water temperature, the tube spacing, diameter, and depth, and it outputs estimated design values for surface heat flux, hydronic heat capacity, water flow rate, surface temperatures, and you can also visualize the design space. So as you can see from this animation, you can see the interaction effects from 2 or 3 parameters at a time. So what you're seeing here is how certain parameters affect the total surface heat flux of the system. So right now we're seeing how the supply water temperature affects the total heat flux. And you can also visualize a 3D space or a 3D surface to see what the effects are that will help you for the design. So now let's take a look at the transient section of the tool. So the transient calculations are based on over 2.5 million Energy Plus simulations, and the results of these simulations are available to you by selecting a few key input parameters arranged on the left-hand side. And one of these important parameters is time. You can select the time your radiant system starts operating and for how long. Time is an important parameter for radiant systems that have their tubing embedding in the concrete and other high mass materials because as we discussed earlier, With high response times of these systems, it's really difficult to try to predict what the effect is going to be from this high thermal mass system. And by including time, we can visualize 24-hour cooling design day profiles, and thus you can use this functionality to see how load shifting strategies impact the space temperatures. So here on the top right graph, we have the surface heat flux in red, the cooling plant rate in blue, and the heat gains of the zone in green. And in the bottom graph, we have the resulting operative temperature. And so Saeed likes to use these tools with his engineers and clients to visualize and assess the feasibility of different design concepts. But so he really enjoys these tools and gives us a lot of feedback on how to improve them too.
Yeah, if you guys are interested, please scan this barcode. It takes you to CBE tools. You can see the 3 tools. This one, I really like this last RAD tool, because sometimes I talk to the mechanical engineers and they're not sure if they want to go with radiant cooling or not, and they want to talk to the client. So this gives them, let's say, phase 1 calculation to give them an idea, okay, if I apply radiant cooling in this room, how much energy I want to need, how much I gain from this, and in that case, they have a topic if they want to go quickly to a meeting, to discuss it. But keep in mind that we, as a PEX A manufacturer, as I said, we are focused on top-notch engineering service. We also provide design and engineering service on the projects that are using our product for the radiant cooling application. Again, feel free to scan that one. It doesn't matter what region you are in North America, you can get connected to one of our greatest design team members. To wrap up our, let's say, discussion today, I have some, again, project samples, because these are in practice, and I would be more than happy to talk to you about this if you had any question. Like, this is one project that I really like, is in Toronto. It's the YWCA. It's in a very high density area of the town, which again has a good value for lead because of the transportation and everything. But considering all of that, it's a tab system, so dual type of a heat transfer. In a normal day, it was calculated, if it was like unidirectional, it was supposed to provide 30 BTUs in heating mode, and as Carlos explained, like maximum 15 BTUs in cooling mode. But since we are using a tab system, two-phase, let's say, slab, we are getting almost 50 BTUs per square foot and 30 BTUs in the cooling mode, which is a big deal. They have 90 geothermal wells underneath the parking, each 150 meters. And they're delivering 3 million BTU per hour. How's that? You are an expert, okay. And the whole project, we're able to achieve 45% reduction in carbon emission, which is a big deal. And also, since we were able to downsize the air system, it eliminated purchasing of 1,200 air filters per year, which the maintenance guy, they love that idea. Again, if you want more information, please scan this barcode, and it takes you to the page. Another project that we are working in LA area, you want me to go back? Okay. It's the Lucas Museum. It's still under the construction. They are thinking of getting to 30% of the reduction in carbon emission by the time of completion. It's a unique design project. You can see this is what they're expecting to see. It's trying to achieve LEED Gold. It has, again, geo-exchange, and it's a radiant heating cooling project, natural ventilation, garden roof, and again, gray water harvesting, which is the reuse of any rainwater system. And again, you want more information, please scan this. This is, I can't wait to see this project.
Yeah, it's really cool.
Yeah, it's a very cool project in LA.
You like Star Wars, you like that building.
Yeah, okay. And this is another project of us, we call it HATS, or High Altitude Aviation Training Center. This is for the National Army Guard in Colorado. That's a dry area, so radiant cooling was a perfect match. You can see it's a big maintenance room there with big overhead doors. So they technically bring the choppers or the aircrafts from that overhead door inside to fix. And you can say if they, for example, focus on forced air and heat up the place, they open up one of the doors and bring one airplane in, everything is lost. So we are focusing on, on the surrounding areas again by using gradient. So if they bring in one aircraft, take your time, okay? Your phone calls, it's your wife, answer your phone. You have time. You have these surfaces as the generator of heat or absorbent. So you're gonna be fine in terms of the thermal comfort. It also has a snow melting on the aprons, and we use the pre-insulated tubing to bring energy from, let's say, central heating and cooling plant, which was a little bit far from the, the maintenance room. Again, for this, please check out this link. This is a very nice project. I really like it. And this one is in my neck of the wood. We designed this with Triple M Group. Now it's bought by WSP. It's a Pacific Autism Center. It has a LEED silver with over 30,000 feet of radiant heating and cooling tubing. This project was able to address the need for the children with the autism disease. It was a silent operation. What good thing about radiant system? It had steady, cooling, steady, let's say, distribution of cooling and heating, and uniform floor temperature, because those kids are very sensitive to these elements. This project was finished with $27 million, which 20 million of this project was provided by government. Again, following the whole green initiatives and the way that they're helping the, children with disease. It was one unique project that I was involved in. Again, please check this QR code if you wanted more information on this. And that takes us to our last slide. You can find our info to our LinkedIn. Feel free to, connect. We would be more than happy to be connected with you guys. And with that, if there's any question, we would be more than happy to address it.